All right, let's look at some equations that use square roots. In all of these, we've got variables with some root issues. Just a second ago, I talked about that 2 cubed was 8, so the cube root of 8 is 2. That idea is that radicals and exponents are opposites of each other. They're inverses of each other. So to get rid of a square root, see my x is inside the square root, so I need to get rid of that. I'm going to square both sides. So when I square both sides, the square and the square root cancel each other out. So what I'm left with is x equals 25. So the way to get rid of a square root in order to solve for x is to take the square. We'll do the same thing over here. So I'm going to square both sides. The reason I have to do it to both sides is because what I do to one side, I do to the other. So now I'm left with negative x is equal to 25. So I still need to get x by itself. So I'm going to divide by negative 1. That's going to get rid of that negative sign in front of x. So I'm going to get an answer of x equals 25. So that's my, x equals negative 25. That's my final answer for this one. Now my third example down here, it's a little tricky. Square roots cannot equal a negative number. They're technically called imaginary numbers or complex because they don't exist in our world. So whenever I see the square root equals a negative number, we say this does not exist because we don't have to worry about imaginary numbers in our class, which is nice. So we're not going to do that. Now my negative can be inside. That's okay. I can still solve. It just can't be outside. So this one doesn't actually have a square root, but it does have a square. So to get rid of a square, I do its inverse or its opposite. So I take the square root. Just like above, a square and a square root cancel. Same thing, a square and a square root cancel. So I'm left with x equals the square root of 2. Now whenever you are taking the square root, it wasn't in the problem, it was what I wrote or you wrote, then we have to include plus or minus. That's because when we square a number, it takes away the negative. Negative 2 squared is 4, and so is 2 squared. So I have to worry about that plus and minus. A few more problems about these irrational numbers. So these last two don't have anything to do with square roots, but they do talk about irrational numbers in general. Remember, square roots are irrational numbers. So I have to come up with irrational numbers between 6 and 9. There are a couple ways to do it. This first one is to think about these square roots again. So 6 is the same thing as the square root of 36. And 9 is the same thing as the square root of 81. So just come up with any square roots between these two numbers. Don't use perfect squares, so don't use the square root of 49 because that's 7, but you can come up with anything else. So, I don't know, the square root of 37, the square root of 53, again, anything between these two square roots, or the square root of 80. You can even look just like that. So here are 3 irrational numbers between 6 and 9. Well, I'm not going to use the square roots for these decimal representations here. These are not irrational numbers. These are rational numbers. We could write them as fractions. We already did that in section 7.3. But this is 0.44444 forever, and this is 0.45454545 forever. I'm just going to come up with something in between these. So I'm going to write out a couple decimals of each of them, just so we can see it a little bit better. So my first one is 0.4444, and my second number there is 0.4545. So I'm going to have anything that starts in between these numbers. So I might start it as decimal 4, 4, and then I might put something like 7. 4, 4, 7's between 4, 4, 4 and 4, 4, 5. Sorry, between 4, 4, 4 and 4, 5, 4. And to be irrational, it can't have any patterns. So I can come up with whatever crazy thing I want after this. 8, 9, 3, 2, 6. And then I want to make sure and show that I know irrational numbers continue on forever and ever. So I'm definitely going to put this ellipse here at the end. Do not forget that. If you forget it, then this becomes a rational number. It's a really big one, and it would have a huge denominator, but it would be rational, so you have to put the ellipse. Also could do this kind of a tricksy move. Again, I'm going to start with this 4, 4. So that's in between 4, 4, 4, 4 and 4, 5, 4, 5. And then I could have this pattern. Maybe I would put, I don't know, I'll choose a 6 here. And then I could write 3 4s instead of 2, another 6. And now I would write 4 4s and a 6. Now, this technically is an irrational number. You might say, but it looks like a pattern, just like the things that are underneath my repeatants right here. But I can't repeat this. If it's 44, there's no 6. If it's 4, 4, 6, right here, this isn't 4, 4, 6. It's 4, 4, 4, 6. And if you say, well, this is that 4, 4, 6 is right here, well, I would have left out that one. I cannot write this under the repeatant. That's what makes it irrational. So I can come up with a crazy digit like this one that has no sort of pattern. And I can come up with a decimal like this one who kind of has a pattern, but it doesn't repeat. I can't write it under the repeatant. I do have to remember anytime I'm going to write the decimal representation to make sure include the ellipse on the end so I know that it's an irrational number.